In the name of Allah, Ahmed Hassanin with you. In this course, I will discuss advanced concepts in grounding and fault mitigation. Of course, everyone knows that the electrical network is not always stable, and therefore faults or short circuits can occur in any part of the network. Naturally, when a fault or short circuit occurs, extremely high currents will flow. But the important question is, can protection devices effectively safeguard the electrical network from the damages caused by these faults? To answer this question, we must first understand how the neutral point is grounded, a process known as system grounding. It is extremely important to recognize that the method of grounding the neutral point plays a crucial role in the behavior of the electrical network during faults, primarily in limiting overvoltages and improving the performance of protection devices in mitigating various faults. Therefore, selecting the appropriate method for grounding the electrical system is crucial, both from a technical and economic perspective, as well as in relation to its intended purpose. Through this course, I will explain the following. I will begin the course with a quick overview of the fundamentals of short circuit current calculations. For more details on these calculations, you can refer to the previous course, which covers short circuit current calculations in electrical power networks. Next, I will discuss example 1. Using the power system shown in the diagram, calculate the short circuit current at points A, B, C, and D, given that the total resistances R are measured in milliohms, the total reactances X are also measured in milliohms. After that, I will discuss a very important topic in this part of the course, short circuit currents in isolated networks. I will begin with an introduction to illustrate this concept. Next, I will discuss earthing or grounding impedance. Then I will discuss example 2. In example 2, we'll learn how fault currents can be controlled by adjusting the neutral grounding method. Specifically, we aim to calculate the required earthing reactance for a generator to ensure that the ground fault current at its terminals does not exceed 60% of the symmetrical fault current. Then I will discuss ungrounded or isolated systems. I will also talk about a very important topic, which is the ground fault in isolated unearthed systems. After that, I will discuss example 3. The figure in front of us shows an ungrounded generator supplying a load through a transformer and a transmission line. If a ground fault occurs at point F on the transmission line, we aim to construct the simplified equivalent symmetrical component circuit, which consists of the positive, negative, and zero sequence components. Calculate the fault current using the symmetrical components method. Discuss the physical and protection implications of single line to ground faults in ungrounded systems. Understand the impact of system capacitance and how it is measured. Explain the behavior of the neutral point during ground faults in ungrounded systems. Next, I will introduce you to some important effects that can occur when a ground fault happens. Then I'll talk about transient overvoltages and how they occur in ungrounded systems. Next, I'll cover the phenomenon of arcing ground, what it is, how it happens, and why it can be dangerous. Then I'll discuss an important phenomenon known as the second short circuit. Next, I'll talk about the phenomenon of false starting in motors. After that, we'll begin the introduction to grounding in low voltage systems. Then we'll discuss the primary objectives of system grounding. Next, we'll explore experience-based guidelines for grounding, starting with industrial systems. We'll continue with experience-based guidelines focusing on transmission line grounding. Then we'll discuss natural capacitances in electrical networks. Next, we'll talk about grounding transformers and their roles in electrical systems. Then we'll explore how grounding transformers can be used to limit fault current. After that, we'll discuss the zigzag grounding transformer and its key considerations. Then I'll introduce the topic of grounding methods. I'll begin with the first type used in low voltage networks, ungrounded networks. Then we'll cover the second type, direct and effective grounding. After that, we'll discuss the third type, high resistance grounding. I will then talk about the final recommendation for the types of grounding used in low voltage networks. After that, I'll introduce the grounding methods used in medium voltage systems, I'll begin with the first method, ungrounded systems. Then the second method, solid grounding. Then the third method, low resistance grounding. I'll follow with a discussion on protection schemes used in medium voltage systems. The first protection scheme is the residual relaying scheme. The second is the ground sensor scheme. The third is the neutral ground scheme. Then I'll cover the fourth grounding method, high resistance grounding. The fifth method is reactance grounding. The sixth and final grounding method in this category is ground fault neutralizer grounding. After that, I'll introduce grounding system circuits. We'll then discuss grounding system circuits in more detail. I'll follow this with a discussion of general guidelines. Then I'll talk about grounding systems in hazardous areas. After that, I'll cover grounding and the ferroresonance phenomenon. Then I'll provide additional notes on ferroresonance. Next, I will introduce the ratings and specifications of grounding devices. I'll then discuss the specifications and ratings in more detail. I'll present the steps for selecting and determining ratings for the first method, grounding by reactance. Then, for the second method, grounding with low resistance. Followed by the third method, high resistance grounding. After that, I'll discuss example 4. The figure shows a generator rated at 7,500 kilovolt amperes or kVA with a rated voltage of 11.5 kilovolts. This generator is equipped with surge capacitors that provide protection against voltage spikes or surges. It is grounded through a high resistance connection, and this connection is made via a distribution transformer. Now the system includes several components, each contributing to the overall zero sequence capacitance. The capacitance values, all given in microfarads, are as follows. The generator itself has a capacitance of 0.320 microfarads. The surge capacitors connected to the generator contribute 0.250 microfarads. The generator terminals add another 0.060 microfarads. Finally, the power transformer contributes 0.004 microfarads. With this information, we will proceed to calculate the total zero sequence capacitance denoted as C0. Next, we'll calculate the capacitive reactance, XC0, based on this total capacitance. Then, we'll determine the capacitive charging current labeled as IC0. Following that, we'll calculate the grounding resistance on the low voltage side. This is based on acceptable power loss in the system. We'll also determine the required rating of the grounding transformer considering the expected fault duration. The result will be expressed in kVA. And finally, we'll take a step back to understand and justify some of the design decisions made here. Why were specific voltages chosen for the system? Why are certain protection strategies recommended? And how are overload factors accounted for in the design? Next, I'll present the steps for selecting and determining ratings for the fourth method, grounding with a zigzag transformer. Then I'll discuss example 5. The figure shows a delta system that requires a neutral point, which can be grounded using an outdoor zigzag grounding transformer and a grounding resistor. The system voltage is 2.4 kV and is connected in a delta configuration. The symmetrical fault kVA is 150,000 kVA, means 150 MVA, and the maximum current allowed to pass through the grounding resistor is 2000 amperes, which is approximately 5% of the symmetrical fault current. The objective is to calculate the appropriate reactance value for the zigzag grounding transformer, as well as the value of the grounding resistor, RG. Thank you for your attention. See you in the next lecture.